Hi everybody, Physics Ninja here. Today what I want to do is I want to solve a circuit with a couple different sources. I have a circuit here that's shown it has a constant voltage source and it also has a constant current source. What I want to do with this circuit here, which also contains two resistors, I want to solve it using three different methods. The first one is just the standard Kirchhoffs methods. We're going to apply the KVL and KCL law in order to analyze this circuit and define the current through every single branch of the circuit and also the voltage across the resistors. In the second part, what I want to do is I want to use an advanced technique called voltage node analysis or mesh analysis in order to analyze this circuit. And in the third, I'm going to use a principle called superposition. Again, we're solving the same circuit, so we're going to get the same answer at the end of each solution. However, you're going to see how each solution is applied to solving the same problem. So hopefully you find this useful. Again, if you like the video, give it a thumbs up. If you like what I'm doing on my channel, consider subscribing. If you have any questions along the way, feel free to ask them and leave them in the comments section below. Let's get started. Okay, so before setting this up here, I've assigned some values here that we're going to use in determining the current in each branch, and I'm also going to look for what is the voltage at this particular node here. I'm going to call it node E and just give it some label. All right, so the first thing, I have a 8-volt power supply over here, and I also have a constant current source that produces a constant current in this outer branch of 2 amps. I've got two resistors. This one's a 5 ohm resistor and a 3 ohm resistor. And I've set a ground value down over here. So the first thing we're going to apply is Kirchhoff's rules. We have KCL, which is the current law. Okay, I'm going to apply that here. Kirchhoff's current law basically says find a node in your circuit, and I'm going to define the node right here at point E, and it says whatever current flows into it has to be what's flowing out. So in order to do this, we have to look at some directions. So I'm going to assume here that there's a current in this branch, and I'm going to call that current I1. I'm also going to assume that current I2 is flowing down. And again, I have a current I, which is already here, and I know the current I here has to be 2 amps because that's fixed in this outer branch. So the KCL law, or Kirchhoff's current law, would basically say whatever current flows into this junction here has to be the current flowing out. So if you look at what's going in, there's I1 that's going in. Let's switch the colors here. And I also have the current I of 2 amperes that's also flowing in. That has to be equal to the current flowing out of the junction. Current flowing out of the junction is I2, and that's it. There's this KCL law. The next thing I want to do is I want to apply Kirchhoff's voltage law, which basically says you start at a point. In this case, I'll start down here at the bottom. And again, if this is ground, that means this point here is 0 volts. So everywhere on this side is 0 volts. The KVL law says if you complete a loop and you come back to the same position, the sum of the voltage differences across each element that you encounter, if you sum all those up together, they should be equal to 0. So the way it looks like here is the first thing I encounter is a power supply, and it's a 8 volt. So this side here is say minus, this side here is plus. So as I cross that power supply, I get an increase in voltage or a potential difference of 8 volts. Next thing I do is I cross a resistor. If I cross a resistor in the direction of this positive current here, there is a voltage drop across that resistor. And the voltage drop is given by the resistance R1 multiplied by the current I1. And the next part here, now I'm going to go to this junction E and I'm going to go down. I'm going to go down through the resistance R2, and what I end up doing here again is a voltage drop. This is at a higher potential than the lower point of that resistor. And now you get R2 multiplied by the current flowing through it, which is I2. Now I'm right here and I go back to where I started right here. So that means if I go back to where I started, the KVL law says, well, all those differences should be equal to 0. Each charge has to have the same amount of energy. Whatever I gained here, I've lost through the resistors. All right, so those are the two laws. And now if you have a look at what are the knowns and unknowns, basically I want to solve for I1 and I2. And these are really the only two unknowns in these equations. So if I just write that down, the unknowns are simply I1 and I2. And once I've determined I1 and I2, I can easily go back and solve for the voltage at this point. because I could just do kind of a start at this point, look at the potential difference across here, and I can easily calculate what the potential difference is across this resistor if you know the current. All right, so let's go see how we would set up our system of equations in order to solve for this. This is simply algebra at this point. So what I'm going to do at the beginning here is I'm simply going to do a little bit of algebra in order to solve for I1 and I2. All right, the easiest thing to do here is maybe use equation 1. You see equation 1, I have I2 all by itself. And what I'm going to do is I'm simply going to substitute this value of I2 inside the KVL law. And if you do that, this is what it looks like. So equation 2, let's just call it 2 prime, would simply become the voltage of this power supply minus R1 I1 minus R2. And now instead of writing I2, I'm simply going to substitute that for I1 plus the current I. And now that must be equal to 0. And now if you have a look at equation 2 prime over here, the only unknown in my equation is I1. So in principle, you should be able to solve for this. So in order to solve for this, what we're going to do is we're going to group together all the terms with I1 in there. So there's 2 of them. So again, simply looks like this. Minus. Now I'm going to group together the terms with I1. You see here you have R1 plus R2, and all of that gets multiplied by R1. And now I'm still left with this term that multiplies the current in this outer branch over here. And that's minus R2 times the current I equals to 0. Again, the only unknown here is I1. You should be able to solve for this, bring it over to the other side, and divide by this resistance. So this is my final expression. I'll go ahead and move it over here. It says that I1 should be equal to V divided by R1 plus R2. And now minus another factor, R2 divided by, again, R1 plus R2. And that gets multiplied by the current I. Again, everything now on this right-hand side are simply numbers, and now I can simply substitute the values. So the voltage V is this 8-volt difference from the power supply. R1 plus R2 is also 8 ohms. And now minus R2 was 3, and divided by, again, 8. And this this constant current source produced a current of 2 amps. So the current I1 at the end, plug that in your calculator. What you should get is 1 for the first term. And here it's minus 3/4 or minus 6 over 8. Okay, so what we're left with here at the end should be 1/4, which is 0.25 amps. All right, now that you know the current I1, it should be pretty straightforward for you to evaluate what is the voltage over here. All right, if you wanted to solve what is the voltage over here, all you have to do now is just do a partial loop. You start over here. I go over this 8-volt power supply, and then I get a voltage drop, right? So this is what I would kind of write down. I would say when I first cross this power supply, I get plus V of the battery, and then when I go across this resistor in the direction of the current, I get a voltage drop which equals to I1 multiplied by R1, and that there has to be equal to the potential at point E. So this equation here, hopefully you understand this one. So this allows me to find what is the voltage here at point E, because again, I know everything else. So let's go ahead and substitute everything we have. So this simply looks like 8 minus the current I1 is what I just solved for, 0.25. And now multiplied by the resistance R1, which is 5. Again, put all this in your calculator, and what I end up getting is 6.75 volts. That has to be the voltage here at point E. All right, so let's go ahead and just box that up. And we can go write it on our diagram. So this guy here is 6.75 volts. All right, I guess the last part we could have solved for now is what is the current across this R2 resistor, and that's simply I2. And for that, I guess the easiest thing to do now is simply just to go back to our KCL law, because since we know I1 and we know I2 is 2, it should be pretty straightforward to solve for what the current I2 is. Let me go ahead and do that right here. So the current I1 was 0.25 amps plus the current I from this constant current power supply here was 2. And now what I'm left with is 2.25 amps. That's the current in that middle branch of this circuit. And that's it. This is how you would apply Kirchhoff's rules in order to completely solve this circuit. Only took about a page. It was a little bit of algebra, but pretty straightforward. All right, we'll now solve the problem using the voltage nodal analysis, or the node method. And the node method, at the heart of the node method, is really our Kirchhoffs current law. If you remember, it says whatever current flowing into a junction, in this case, which is I1 plus the current I, has to be equal to the current flowing out of the junction. Now, once you get good at this method, you basically don't even write the KCL law anymore, because it's just kind of so straightforward that usually you skip this step in the solution. But this is really at the heart of it. And what this method, as the name implies here, the method is most useful to find the voltage at any node. And in this case here, the node of interest is going to be this one. If you're able to quickly determine the voltage at any node, you can then find the current. So at the heart of this method here, let's consider the simple case down here at the bottom, where I have a voltage V1 at one point, a voltage down at the other end of the wire, which is V2. So there's a potential difference of V1 minus V2, and the current here, you can simply write down the current right away as being the voltage difference, which is V1 minus V2, and divided by the resistance. Okay, you're automatically able to write down this expression for the current, and that's what we're going to do with each one of these currents over here. At least both of these. This one here, there's nothing to replace it with because it's a constant current source. But if we can replace both of these values with a potential difference, you're going to see we're going to be able to solve for the voltage at point E right away. Okay, so to set this up, again, remember we have 0 volts down here, so that means all of these 3 points here have to be grounded. They're all at 0 volts. So that means if I go on this left branch over here, that means that the voltage right here at anywhere along this point here has to be 8 volts. And there's going to be a potential drop, and the voltage over here at the node is E. So let's have a look now. What would be the current I1 if I think about it in terms of writing it through something like this? How can I substitute the value of I1 directly for a voltage difference divided by a resistance value? In this case here, it would look something like this. So this guy right here should look like the voltage of this power supply, right? And minus the voltage at point E, and divided by the value of the resistance, which is R1 in this case. So this here should be really my expression here for the current flowing through this resistor. Plus, again, this is not an unknown. In this case, it's simply 2 amps, so I'll just leave that as the current I. And that there has to be equal to, let's think about another way of writing the current through this middle branch over here. Again, if you consider the similar analysis to the simple case over here, you should be able to write it as something like this. It should be E minus, again, this point here is at 0 volts. I mean, I can write it for now, and divided by the resistance. In this case, it's the resistance R2. So let's go ahead and cross out that 0. We don't really have to worry about that. In principle, I didn't even really have to write this down. However, have a look at my equation over here. Let's call this equation 1. Okay. Equation 1, the only unknown in equation 1 is the voltage at point E. It appears at 2 different positions. However, it really is the only unknown here. So it should be pretty straightforward in order to solve this. So this is what I'm going to do now. All we have to do now is do a little bit of algebra. So let's go ahead and just rewrite this a little bit. I'm going to write this as V minus E. Keep this term here the same. Plus the current. And let's just bring this term here on the other side. So it's minus E over R2. And that there must be equal to 0. All right, we're going to do a little bit more math now. We can group the terms here that have E. And then we can factor it out. So what you end up getting here is V divided by R1. That's this first term. What else? Plus the current I. I'll just keep that term by itself. And now that there should be equal to, if I group both of those terms with the E and I bring them on the other side, what you end up getting here is 1 over R1 plus 1 over R2. That should look like a familiar expression, and all that gets multiplied by the voltage here at the top. Okay, so again, all we have to do now is a bit more math. I'm going to put this on a common denominator. The common denominator is going to be R1 multiplied by R2. And here I'm going to be left with R1 plus R2. And again, all that gets multiplied by E. All right, at the end, I can write one final expression for E. So the voltage at point E, Again, you simply have to multiply through or take the inverse of this term over here. Now what you're left with is that one of those R1s is going to cancel with this term. So you're going to be left with something like this, R2 divided by R1 plus R2 multiplied by V1, and then plus another coefficient term, which is just flipping this term upside down, and divided by the total resistance. And all this gets multiplied by the current. All right, let's go ahead and look at this expression here. This is the voltage here at point E. Again, the way I've written it here, I haven't substituted in the numbers. And if you're not new to this, I would suggest you don't substitute in the numbers right away, because you're going to see some cool things that are going to happen in just a little bit. Actually, there shouldn't be a subscript over here. That should just be the voltage V. So all you have to do now is substitute in our values. So you see here we have a term in the front. The term in the front is R2, which is 3, and divided by 8, multiplied by the voltage, which was 8, and plus, if I multiply those values of the resistances, you should get 15, and divided by the sum, which is 8, and all that gets multiplied by the total current, which is 2. All right, at the end, you substitute in everything in the calculator, and lo and behold, you get 6.75 volts. That's the exact same number we had previously, using a different method. Okay, so hopefully this highlights how you set this up. Now I want you to focus on this equation here in this blue and red box over here. This is really at the heart of the next method, which is the superposition method. All right, so let's go to the next page and I'll show you how to apply superposition to this problem. All right, the last method that I want to look at here is applying superposition method to solving this circuit. And in order to do that, I want to look at the solution that we obtained for this voltage at this node over here in the circuit. And this was our solution. Now have a look at it. What we have here is the terms in the brackets are simply numbers. We can call these coefficients. And these two terms over here are source terms. There's a source term for voltage. There's also a source term, in this case, for current. So we have two source terms because the circuit involved has two sources. And the voltage at any point, actually in this case there's only one other node of interest here, can actually be written as some coefficient multiplied by one of the source terms plus another coefficient, let's call it alpha 2, multiplied by the other source term in the circuit. If I had other branches with other voltages and constant current sources, I would simply have other terms here with other coefficients. All right, I could have a different voltage, I could have another current source somewhere in the circuit. I would simply have additional terms. In this case, I only have two, therefore there's only two terms. So the superposition method is a quick way of obtaining, well, what are these coefficients that go here? Right? In this case here, it's simply this ratio of resistors, right? But if we had a quick way of determining what are these coefficients, alpha 1 and alpha 2, then right away I should be able to write down the voltage at this particular node. So what we're going to do here is we're going to show you a method that allows you to quickly determine the coefficients in front of each one. And what you end up doing is you end up turning off one of the voltage, one of the sources, and you solve a simpler circuit one at a time. And then after, what you end up doing is simply adding up the solutions of the simpler circuits. So let me show you what I mean by that. All right, so again, looking at this voltage at node E, we have the superposition of the solution that only includes the voltage term, and we add that to the solution where we only include the current term. So what we're going to do here is, if we're able to actually solve a simpler circuit, and we're able to obtain this first term, and then solve a secondary circuit and obtain what the second term is, then what we're going to do is we're going to simply add up both of those solutions. So this is going to be solution 1, and this is going to be solution 2. Okay. And what we're going to do to get solution 1, what we end up doing is we want to eliminate all the other terms. So how do we do that? Well, we don't want any current sources, So we're going to end up solving the circuit when the current I equals to 0. And then we're only left with this first term. To get solution 2, what we have to do is we want to turn off all the other sources. So in this case, what we're going to do is we're going to turn off the potential difference of this power supply. We're going to set the voltage equal to 0. And anyway, and then what you end up doing is you simply add up the two solutions that you're going to get. Right now it seems like a lot of work, but you're going to see it ends up really simplifying the circuit. And at the end, you simply add up two simple solutions in order to get the more complex solution that we have here at the top. All right, so to apply the superposition method, again, what we're going to do now is solve two simpler circuits. The first one that I'm going to solve is the case where I turn off one of the source terms, and I'm going to turn off the current source. So the way you turn off a current source is by setting the current equal to 0. So in this case, what we end up doing is simply making an open circuit over here, right? If this is open, if we produce a break here, there won't be any current flowing in this section. And then what we're left with is simply this little circuit over here on the left-hand side, and this one's super easy to solve for. Because all we have is one power supply, and we have two resistors, and we're looking for, again, what is the voltage over here at this node? Well, you know that this is 0 volts down here, and it's going to be the same current everywhere, right? So the voltage over here, if I start at this point and I go across the resistance R2, and I end up at 0, you know that E, the voltage at that point, minus the voltage drop across this one, which is whatever current is flowing through that, just call it I1, multiplied by R2, this here has to be equal to 0. Right, so the voltage at point E for this simpler circuit now is simply the current I1 multiplied by R2. Now it's kind of useful to eliminate the current I1 and write it in terms of the power supply and the other values of the resistors. So in order to do that, again, just remember that both of these resistors are now in series. So the total resistance is simply R1 plus R2. And that means that the amount of current that's flowing in this circuit, in this case I've just called it I1, is simply the voltage divided by the total resistance, which is R1 plus R2. All right, now if you put everything together, at the end of the day, what you end up getting is R2. And instead of having the current I1, let's just substitute it by the value over here, which is the current flowing through this left branch over here. So what you end up getting is the voltage V and divided by the total resistance. You should note actually that the voltage here at this node, this is simply a voltage divider. So this should be something you should be familiar with. Writing down the voltage at this point is pretty straightforward if you have simply two resistors like this. All right, so this is going to be our first term, right? And if you look at the solution above, you'll also notice that it's the exact solution that appears right here. However, I'm not done. I've only solved the circuit now when I've turned off the current source. What I have to do now is also solve the circuit when I turn the voltage source off. So let's see how you do that. All right, in the second case, what I want to do now is I want to turn the voltage source off. Now what I'm going to do, how do you do that? In order to turn off a voltage source, what you end up doing is you don't want a potential difference across the ends. So what that ends up looking like now is what you want to end up doing is you want to end up shorting this. All right, if I short this, just make a connection with a wire, there's now no voltage difference here between this point and that point. So you end up kind of shorting connections where you have a voltage power supply. Okay, so all we have to do here is that's the way we're going to turn V off. And now what we want to do again is go back and solve a simpler circuit. In this case, we have a constant current source and we have two resistors. And we want to find what is the voltage here at this point. And we're going to add that to the previous solution. So in this particular case now, all we have to do is note that, well, once this current over here, which was 2 amps, all right, once the current here flows up here and reaches this junction over here, it's going to split into different parts. However, you should note that both of these resistors now, since this is only a wire in this simple circuit, that R1 and R2 in this configuration are simply in parallel with each other. So what you can do actually is replace this with a simple current source And instead of, here's point E. And now all we're going to do is simply replace, instead of R1 and R2, I can replace this with one effective resistance and then go all the way back to my constant current source, which was 2 amps. This here is simply an effective resistance. And the way you find the effective resistance, if I have R1 and R2 in parallel with each other, is simply 1 over R effective equals 1 over R1 plus 1 over R2. If you put things on a common denominator and you invert it, what you end up getting is that the effective resistance ends up being, you multiply them and you divide it by the sum. Okay, so now it's pretty straightforward to find what is the voltage difference across this effective resistance. Because remember, we have 0 volts down here. This part here is grounded. So the amount of current flowing through this effective resistance has to be 2 amps in this simple circuit. So that means that the voltage at this point is simply the current multiplied by the resistance. That's just given by Ohm's law. So right away, you should be able to write this, right? It's the current I flowing through it and multiply by the effective resistance, which is R effective. So you can write R effective is R1 multiplied by R2 divided by R1 plus R2 and multiplied by the current. Again, this is the voltage E obtained from a simpler circuit where we've turned off the voltage source. Now what you have to do at the end, you have to do superposition. We need to add both of our solutions together in order to get the full solution of the circuit. So let's go ahead and do that. Okay, so to get the total voltage here at point E, what you end up doing is adding our first solution, and that was the solution we obtained when we turned off this constant current power supply. And again, I just got that simple first term. And all that was multiplied by V. And plus, now the second solution, when I shorted out the voltage source, I ended up getting this solution over here for the node voltage over here, R1, R2, divided by that total resistance and multiply by I. Okay, we say that this solution here is linear because look at the terms. It's always linear in the source terms. There's no terms here. This is really important. This is why this solution actually works. There are no terms in like V squared. There are no terms in I squared. There are no terms that multiply V times I in this voltage at any node. Right? There are none of these terms. These are higher order terms, and none of those terms appear here in the solution, and they never will for linear circuits. And those are the cases where I could apply this superposition method. So again, to recap, all you do is you look at all the different source terms and you turn them off one at a time, and then you simply solve the circuit. And that'll allow you to find right away the voltage at any node in your circuit in a quick and efficient manner. And once you get really good at noticing some patterns, and one of the patterns you're going to see a lot are voltage dividers. So if you're used to kind of working with voltage dividers, you'll kind of see this first term quite a bit. Anyway, it just takes a bit of practice, and then you'll be able to solve any problem in a little amount of time. All right, folks, thanks for watching. Hope you enjoyed the video.